Good morning and welcome everyone, and thank you for joining us for today's webinar, during which we'll share with you several key insights about chlorine dioxide and its role in modern water treatment. And for these insights, you'll hear from three experts today. First, we'll begin with Scott Glenn, a senior chemist, who will walk us through the core properties of chlorine dioxide and its history in drinking water treatment. Next, Dr. Zach Lee, a senior process engineer, will discuss how chlorine dioxide can enhance unit operations to improve overall water quality. And finally, Dr. Alan Burke, a chemical engineer, will cover regulatory considerations and methods of generating chlorine dioxide. Overall, the presentation will take approximately 35 minutes, followed by 15 to 20 minutes of Q&A. We encourage you to submit questions at any time throughout the presentation using the Q&A feature on your Zoom menu, and we'll do our best to address as many as we can at the end. Each speaker today is part of the International Dioxide team, an ERCO Worldwide company with more than 75 years of experience providing effective chlorine dioxide precursor chemistries as well as generation equipment. And with that, let's get started. Scott, we head over to you.
Thank you for the introduction. I'm Scott Glenn, and I will be presenting a high-level introduction to chlorine dioxide and its use in municipal drinking water. My colleagues, Drs. Lee and Burke, will provide more in-depth discussion on those topics. As you can see, there are many markets and applications where chlorine dioxide is used. For today's discussion, we will only focus in on municipal drinking water. Within the drinking water application, there are several areas where chlorine dioxide is used, from disinfection of various types of organisms to oxidation of compounds that can leave stains on fixtures and clothing to leaving a bad taste or odor in the water. The use of chlorine dioxide can aid and enhance many water processes such as coagulation, sedimentation, and filtration, as well as cleaning of the system by reducing and preventing mollusks and other biofilms, all of which can lead to a reduced demand for residual disinfectant and improve overall water quality. We will discuss these uses later in the webinar. Chlorine dioxide is a chemical that was discovered over 200 years ago and only started being used commercially about 80 years ago. While chlorine dioxide has chlorine in its name and structure, it is very different than chlorine. Chlorine dioxide is a gas and is predominantly generated in water, where it remains as a gas and is applied as a solution in most applications. Unlike chlorine, the gaseous form of chlorine dioxide cannot be compressed and shipped in cylinders, which require it to be generated on site. Chlorine dioxide solutions are typically a light yellow-green color, which increases in intensity and color as the concentration increases. Chlorine dioxide is a free radical, which simply means that it has an unpaired electron and wants to react with something that gives up an electron in a true oxidation reaction process. Therefore, chlorine dioxide functions as a highly selective oxidant when it reacts, which can lead to a much lower required dose to achieve the desired effect. Because chlorine dioxide reacts only via an oxidation process, it does not form chlorinated organics, trihalomethanes, THMs, or haloacetic acids, HAAs. In fact, chlorine dioxide reduces the formation of THM and HAA precursors. On the other hand, chlorine, which can react via three different methods, oxidation, addition, or substitution, form halogenated organics, including the THMs and HAAs. Chlorine dioxide is a powerful biocide, one of 4 approved by the EPA for use in potable water disinfection. Because chlorine dioxide remains as a gas dissolved in water, it remains effective over a wide pH range, unlike chlorine and bromine, which become weaker disinfectants as the pH increases. Chlorine dioxide is a broad-spectrum biocide as it is effective against bacteria, viruses, algae, biofilms, and other organisms. Due to the way chlorine dioxide interacts with organisms, oxidizes the basic cell structure, and shuts down its metabolism, It is theorized organisms cannot develop an immunity to it, unlike other disinfectants. In most applications, a lower dose of chlorine dioxide is required to achieve disinfection or oxidation, which translates into being less corrosive than other halogenated products. In the end, chlorine dioxide and its byproducts ultimately degrade into salt, chloride. Chlorine dioxide was first used in the U.S. in 1944 in Niagara Falls, New York for taste and odor issues. Use of chlorine dioxide had a slow growth over the next 30 or so years until the late 1970s when THMs were discovered in drinking water. Health concerns related to the THMs resulted in an increase in the use of chlorine dioxide, with hundreds of water plants using it by the 1990s. And due to regulatory pressures in the late 1990s and early 2000s around disinfection byproducts, DBPs, related to the chlorination, the use of chlorine dioxide increased to over 1,000 facilities in the US and even more globally. With its growing use in disinfecting drinking water, other industries took notice and started using it as an effective alternative to chlorine and other disinfectants. As mentioned previously, there are many locations that chlorine dioxide can be applied to in the water treatment process. In the US, chlorine dioxide is predominantly used for pre-oxidation and primary disinfection, and in a limited but growing market, the supplemental water treatment process. In the pre-oxidation zone, such as the raw water intake to the sedimentation process, where chlorine dioxide is used to oxidize iron, manganese, organic precursors that form THM and HAAs, and to gain early credit for CT. In the primary disinfection zone at the filters and clear well for CT credits and a reduction of chlorine dose leading to lower THMs and HAAs out in the system. In the secondary disinfection zone, the water enters the distribution system where a chlorine dioxide residual can help clean up the distribution system, which results in a longer lasting residual due to biofilm reduction and nitrification control. It should be noted that in the US, chlorine dioxide is generally not added to the distribution system, but is carried over from a primary disinfection zone. In the supplemental or secondary water treatment zones, such as in industrial hospitals and other small applications for potable and processed water disinfection. That is the end of my presentation. I will now turn over to Dr. Lee to discuss in more detail some of the uses previously mentioned. Thank you.
Thank you, Scott, for the nice overview. Next, I'm going to talk about some applications of chlorine dioxide in drinking water treatment. First of all, many US utilities using chlorine dioxide as pre-oxidation to treat iron and manganese from the source waters. Iron and manganese can be either existed all year round in groundwater sources or seasonally in rivers, lakes, and reservoirs during spring fall turnover or in the events of storm runoff. Different approaches have been taken by utilities to treat iron and manganese. Among them, chlorine dioxide is the most effective control. Their dissolved form can be quickly and thoroughly oxidized to solid forms. Any follow-up solid-liquid separation can remove them from water efficiently. These include conventional coagulation, flocculation, and sedimentation, or DAF units, and medium filtration. After chlorine dioxide pre-oxidation, a direct filtration with low-pressure membrane processes such as microfiltration or ultrafiltration can also do the work well. In the meantime, chlorine dioxide inactivates iron and manganese-reducing bacteria. This protects downstream distribution systems from resuspension and release of redissolved iron and manganese ions. Next slide, please. Chlorine dioxide treatment can also control many other taste and odor causing agents. Chlorine dioxide degrades phenols by direct oxidation to form harmless, taste and odor-free compounds. Chlorine dioxide effectively oxidizes hydrogen sulfide and many organic sulfur compounds. Chlorine dioxide and its byproduct chlorite can prevent algae, fungi, and bacterial growth. So overall, chlorine dioxide can play an important role in terms of taste and odor control and color control and the delivery of high-quality product water. Next slide, please. Chlorine dioxide can be applied in preventing biofouling of membranes that are used in reverse osmosis and nanofiltration systems. These treatments are increasingly being used in saltwater desalination, brine treatment, and reclaimed wastewater treatment for potable and non-potable reuse purposes. Microorganisms are very good at developing biofilms at the surface of membranes and feed spacers. To combat biofilm formation, chlorination and dechlorination is often used to disinfect the feed water for these systems. However, even with the chlorination and dechlorination operation, biofouling problems are still quite common. Membrane biofouling is actually considered a major threat to RONF system operation, therefore often requires regular sanitization to control biofouling. However, sometimes in the presence of transition metal ions such as residual iron and manganese, the peroxide or PAA-based sanitization reagents will be detrimental to RO and nanofiltration membrane system. Chlorine dioxide provides a viable solution. Chlorine dioxide pre-treatment has proven more effective disinfection and biofilm control with both media filters and cartridge filters. Chlorine dioxide pre-oxidation combined with low-pressure membrane processes, including microfiltration and ultrafiltration, reduces footprint and increases production capacity and protects downstream RONF units. This is done not only from biofouling control, but also from control of transitional metal ions, including iron and manganese. This can prevent damage to the membrane materials. More recent studies have shown that using chlorine dioxide to sanitize compatible membranes can lead to much longer operational time than by using chlorine treatment. Next slide, please. Another application is nitrification control. Monochloramine is now widely used as a secondary disinfectant in drinking water distribution systems in the United States. However, its associated nitrification issue can cause consumption of dissolved oxygen, alkalinity in the distribution system, and decreases pH, especially localized pH, increases corrosion, and harbors bacterial regrowth, including opportunistic pathogens regrowth. Using chlorine dioxide can help maintain the stability of monochloramine by inactivating both ammonia oxidizing and nitrite oxidizing bacteria in the distribution systems. Chlorite, either as a byproduct from chlorine dioxide or direct injection into the distribution system, can further prevent the regrowth of ammonia oxidizing and nitrite oxidizing microorganisms. This application has been successfully used by many utilities in multiple states in the United States. Next, Dr. Burke will talk about regulations, DBP management, generators, precursor chemicals, and so on. Alan, please take it over.
Thanks, Zach. What Scott and Zach have just shared is a great overview of how chlorine dioxide can be used to improve overall water quality and help maintain consistent operations at a public water system. Now we'll turn our attention towards the primary regulations that have applied to chlorine dioxide over the years. In the late 1980s, a surface water treatment rule was passed that required monitoring the contact time values and calculating them to ensure there was proper amount of contact time of the disinfectant in the water to disinfect appropriately. You can see in the table here that Giardia, which is a harder to kill organism, is used as the base organism, as well as general virus, log kill, inactivation, contact time requirements. And each is dependent on the oxidizer being used. And there are other factors at play, such as pH and temperature, that can affect the contact time requirements to achieve the log kills that the water treatment provider is trying to attain. Chlorine dioxide does stand out for being largely independent of pH, even ranging from 7 to 9. You can see how free chlorine, the dosage requirement for the contact time is about doubled in that case. Ozone is the most powerful oxidizer here, and it has the lowest contact time, but it is consumed very rapidly. Chlorine dioxide does maintain a residual much longer than ozone does, so the achievable contact time in practice can be much longer with a time factor while it's still maintaining low dosage rates of chlorine dioxide. This was enhanced in 2006 when the long-term 2 enhanced surface water treatment rule went into place, primarily looking at surface waters again and cryptosporidium as an even harder to kill microorganism, where chlorine is largely ineffective and UV is somewhat effective and can be put in place, but supplementing UV or other treatments with chlorine dioxide and ozone is much more effective in combating cryptosporidium and these harder to kill microorganisms. In some cases, 3-log inactivation is required if cryptosporidium is detected at high enough levels in the source water. And in general, a minimum of 2 disinfectants are required if cryptosporidium is active at any level in the source waters. And as more groundwater is becoming under the influence of surface water, as municipalities try to use more surface water and use the groundwater as a backup and reserve supply, this becomes more important, and even the groundwater supplies now used are blended with surface water, so these regulations would apply to those waters as well. We've already discussed how chlorine dioxide helps to minimize the halogenated disinfection byproducts that often arise from chlorine treatments. But the main byproduct that arises from chlorine dioxide treatment is the byproduct chlorite ion. So when it reacts with electron-rich compounds in the disinfecting step, it is a pure 1-electron transfer reaction, so very pure redox reaction occurs where the oxidized byproducts are generated and chlorate residual also appears. And generally, about 50 to 70% of the chlorine dioxide dosed into the system can be detected as byproduct in the system. There is also some chlorate that is co-generated as a byproduct. This can be generated from sunlight and UV degradation of chlorine dioxide or chlorite. It can be combining chlorine dioxide or chlorite with stronger oxidizers like ozone, chlorine, or permanganate that oxidize chlorine dioxide or chlorite to chlorate. And this could also arise from generator inefficiencies or chlorate levels in the precursor chemistry being used in the chlorine dioxide generators. But ultimately, all of these salts do degrade to chloride, typical table salt anion, and biological processes can do this, and natural UV degradation of these species over time will ultimately get to chloride. And for this reason, it's really not a bioaccumulative disinfection byproduct, which is of great benefit and overall environmentally friendly. Now, how can oxychlorine residuals be removed if this is a concern? For chlorite, chlorite is more reactive, around a neutral pH than the other oxychlorine species. Granular activated carbon is often used, and it will react there and be consumed. Ferrous iron salts, ferrous sulfate, can be used to knock down the chlorite residuals, and that can be beneficial in coagulation processes, forming ferric iron salts that can then be used in those processes. And also, dehypo operations based on sulfite solutions can also be deployed to lower chlorite residuals if need be. Chlorate and perchlorate are not regulated now, although there are suggested perchlorate regulations coming in future years from the EPA. These are more persistent than chlorite and chlorine dioxide, and they have not typically been present at reportable values in drinking water. And so they can be harder to remove if they need to be. But bioremediation, RO membranes, advanced oxidation processes can be used. If you do try to react directly with a sulfite solution in a normal dehypo type operation, you would typically require a lower pH to help drive that process and oxidize and reduce these compounds. So concerning back to the regulations themselves that were first developed in the 80s and then strengthened again in the 90s. These are the stage 2 disinfection byproduct rules, and the total trihalomethanes and HAAs are monitored to have an idea of the general amount of halogenated organic species that result from the disinfection processes in the plant. At the time, ozone processes were monitored, and a main issue that arose was that bromate can be formed readily if bromide pre-exists in the source waters. So that is also monitored and plays a role here. There's not one disinfectant that's really a silver bullet to prevent all of these, but by using them in combination, you can achieve satisfactory results. Really, the top 3 are not generated from chlorine dioxide usage, so that's a great benefit of having it incorporated to some effect in your plant treatments and having some resiliency around how to treat the source waters. But when chlorine dioxide is being used in the plant, you must monitor for chlorite and chlorine dioxide residuals. So chlorite leaving the plant must be below 1 milligram per liter and chlorine dioxide below 0.8 milligram per liter. Typically, chlorine dioxide is only dosed at about 1/2 to 1.5 part per million or milligram per liter. And so that will basically ensure compliance with these MCLs. Looking at your source waters and a whole holistic approach to how to control the stage 2 disinfection byproducts and adhere to the rules, you really need to look at all the processes in your plant. And there's a lot of synergies that can develop with chlorine dioxide and these other processes as far as helping to optimize the coagulation and sedimentation processes and pull more of the organic precursors out of solution in those steps. That's where using chlorine dioxide as a pre-oxidizer can really be helpful. You can change the point of where the final, chlorine primary disinfectant is applied, try to move that further downstream, have more upstream disinfection and oxidation with chlorine dioxide when those precursors are more concentrated, can be very helpful. And just making sure that ozone and ultraviolet systems, which are more point-in-place treatments, don't really carry any residual. Try to make sure chlorine dioxide is mostly consumed before interacting with those segments in the process train is helpful to prevent chlorate formation and overall water treatment quality to improve that. The figure here on the right is basically showing how a New York utility started with chlorine dioxide treatment, and the total trihalomethanes were greatly reduced by over 50% and maintained that water quality in the second and third years after switching over to chlorine dioxide. A deeper dive into the disinfection byproducts can be seen in numerous studies, but one in particular even looks at, this was lake source water that was also low bromide levels in the source water. And going clockwise around this chart here, you start with the raw water and increasingly higher levels of treatment, ranging from simple pre-oxidation and coagulation, sedimentation, filtration, then implementing granular activated carbon and post ozonation treatments as well. Really trying to look at different pre-oxidation steps and the differences between them. And chlorine dioxide really stood out for lowering the overall genotoxicity of the compounds measured in this study. This study really analyzed all of the disinfection byproducts created in the finished water and assigned a genotoxicity value to each of those chemical species. And basically, the closer to the origin here means a lower genotoxicity. You can see highlighted in yellow how chlorine dioxide helped reduce the genotoxicity overall, which is important for long-term prevention of cancer in water supplies. Now we'll take a step into chlorine dioxide generation methods. Primarily, the top three processes are used in municipal water treatment, which are medium to large-scale water chlorine dioxide generation systems. We refer to these two top chlorite-based methods as two-part and three-part, where the two-part uses elemental chlorine gas to drive chlorite conversion to chlorine dioxide at very high efficiency and low salt production. The main con to this approach is that bulk chlorine gas needs to be stored on site. So if that is an issue for your particular location, then a three-part chemistry can be considered, where liquid bleach and hydrochloric acid are used to convert sodium chlorite efficiently to chlorine dioxide. The main cons here is just having to store another chemical now and monitoring the hypochlorite concentration over time, because it will degrade, especially in warmer climates, and you want to ensure that you're getting proper bleach feed into your system and proper conversion. Sodium chlorite is the most expensive chemical out of these, so you want to make sure you're using that to the best efficiency possible in your system. Both very safe systems overall, especially when using a vacuum eductor system, and we'll get into that in the next slides. The chlorate-based method uses a pre-mixture of sodium chlorate and hydrogen peroxide, and that is activated when mixing with a strong sulfuric acid solution. So this does use a pre-reaction chamber to feed into the water supply. So a little more hazardous in equipment scale, but the precursor has a good cost point, as all sodium chlorite is manufactured from sodium chlorate. So environmentally and cost-wise, there's good reason to look at chlorate-based methods. Although the way it is manufactured, it does carry over, the sodium chlorate does carry over some trace levels of perchlorate and chlorate, out of the generator that needs to be monitored and considered. Again, nothing at reportable levels, but they are there. And the two smaller scale approaches we won't dive into in this talk, but they're basically acid chlorite methods, which has a reduced yield. Only about 80% of the chlorite can be converted to chlorine dioxide, so the operating expenses are much higher. And electrochemical systems typically do not scale up to very high production rates, but can generate very high quality chlorine dioxide, especially if stripping off of the anode recycle loop in these cells. International Dioxide offers several different designs depending on your precursor chemistry being used. These all use eductors to create vacuum to draw in the concentrated chemical precursors into the system. So they have inherent safety, wherein if you lose power or if there's a leak in the system, you're not going to spray chemical out of the system with pumps. The chemical precursor lines are not pressurized, so they will not leak out readily, and everything will be safely diluted if there's a shutdown or emergency situation. Starting on the upper left, a very small system we've commercialized for the acid chlorite chemistry for smaller scale generation rates of about 6 to 30 pounds per day. These can really have no electrical inputs, be very low cost, basically on-off situation with the water supply being turned on and off. And these are lower concentration chemicals, very stable, and a little safer to store in tighter operating environments. Next, the MG2 and 3 basically refer to the 2 and 3 part chemistry systems. These are used in industry and municipal accounts largely. They offer good turn down ratio and a good means to monitor the efficiency of the reaction at the generator. The output concentrations typically of anywhere to 2 to 300 ppm up to 3,000 ppm, and then that feed line will be diluted further to the application point and the desired concentration there. And these can scale from as low as 20 up to 5,000 pound per day with typical turn down ratios of 4 to 1, which can be greater than that if you have some hardware, extra hardware added to the systems. Moving down to the inline system, this is more for industrial applications, but really raises the turn down ratio capability as this is treating the main water supply. The main water header runs through the skid here. So you're really diluting into the full water header application flow in this system. And so the 3-part chemistry can be scaled up higher and safely treat at a higher production capacity. The Byproducts system is shown in the bottom left here. Now we have scales ranging from 30 to up to 2,500 pound per day with turn down ratios of 7 to 1 for each platform. And again, that uses the chlorate based chemistry to drive that reaction. ERCO manufactures sodium chlorite and sodium chlorate, which are used in many applications, and we carry all the EPA and Canadian registrations for drinking water use, as well as NSF certifications, and we adhere to AWWA standards for chlorite manufacturing and distribution. The ERCO Pure product lines are available in several different concentrations for sodium chlorite. The Anthium series is also sodium chlorite based and used for a wider array of specialized applications. And the Byproducts material is what's used for the chlorate based generation methods. And these can be ordered in drums, IBCs, or bulk delivery to the customer site. Apart from supplying the chemicals and equipment, technical services are critical to ensure proper implementation of chlorine dioxide, especially for first-time users of chlorine dioxide. This starts with engineering and equipment design, and the equipment can be tailored to each customer's needs. And we can work with the staff to ensure analytical training is in place so that proper lab techniques are being used to monitor process efficiency. And we can also provide on-site services and emergency support to provide maintenance or get on a call or make a site visit when necessary to help assist and make sure to keep systems online and minimize downtime. So with that, that concludes our presentation, and we'd be glad to answer any questions that folks have.
That's right, Alan. We're going to open it up for Q&A, and if anyone has a question for the team, we invite you to submit it into the Q&A chat feature at this time, and we'll answer them in the order they're received. Again, we invite you to submit any questions using the Q&A chat feature. Looks like we might have a question for someone who raised their hand and I think is now typing in the Q&A chat. All right, we have some questions coming in, guys. First one is, when used as a primary disinfectant, what is the occurrence rate of ClO2 or chlorate chlorite as a residual disinfectant?
I could take that. The accepted value is assume about 70% of the applied chlorine dioxide dose will go to chlorite. Maybe 5% go to chlorate and the rest to chloride. But that all depends on what is the makeup of the water. If the water has more iron, manganese, sulfites in there, more of that will go to chloride. If there's high organics, then you could have more than 70% going to chlorite. The nice thing is, though, that the chlorite does break down relatively quick, especially once it starts getting out into the distribution system. So you can see that number drop off usually very quickly.
All right, great. Thank you, Scott. Next question we have here is, how will chlorine dioxide interact with ferric chloride in a ballasted flock water treatment plant?
Well, ferric chloride is already has basically oxidized to the +3 state. So that should not have any direct reaction with ferric chloride. Ferric chloride is slightly acidic, so depending on how it's mixed in and if it's affecting the pH, the acidity could, in theory, I guess, convert some chlorite back to chlorine dioxide, but not likely at the scales of a drinking water plant.
All right, thank you, Alan. And again, folks, if you have any follow-up questions to what they shared, feel free to resubmit those in the chat function or the Q&A chat function. Next question we have is, what is your recommendation for the best ClO2 generated instrument to get a reading on how much chlorine dioxide is generated and to measure chlorites at POE?
Well, we think the standard is the Optec, which is looking at the absorbance of chlorine dioxide molecule, and they're quite expensive though, and it's really for higher concentrations. So that's where you monitor right at the generator for generator efficiency. Pyxis is also another model, a little lower cost that can be used, and a number of customers have had good results with that device. For lower concentrations, once you're at the low dosage range, 1 part per million and lower, there are some amperometric inline monitors that can be used. The Kunze probe we've had good success with, being one of the more robust instruments in-house. A lot of the other ones tend to be more, lab analytical equipment, maybe not quite as robust. But still grabbing a sample, probably using ion chromatography for the low amounts of chlorite residual for the monitoring your MCL is probably the most reliable method. The Palin test and other amperometric devices can be used, but requires some experience with the analyst to make sure you're getting repeatable values. Those tests. That's mostly for the chlorite residual analysis. Some of those can also do chlorine dioxide residual.
All right, thank you, Alan. We have another question saying, someone here has had a question from a customer raising concerns regarding the sodium chloride impurity when the two-part system is used for pre-oxidation of manganese. Is the impact of sodium chloride that much in potable water treatment?
I can try to answer this one. I don't think sodium chloride would have a much impact in drinking water, especially for pre-oxidation of manganese. Because it's neutral, things to need to be pay attention to sometimes is the presence of actually natural organic matter. If there is too much humic acid or furic acid, people are talking about it. There might be impact of these things to the oxidation of iron. In this case, from field experience, if you add the calcium to increase the hardness of the source water, and then that can solve the problem. So sodium chloride itself, no, I don't think there is a negative impact. Scott and Alan, you have some add-on?
Yeah, I'm not aware of any issue with chloride in the chlorine dioxide being an issue with manganese. In the amount of chloride that's introduced from using chlorine dioxide is usually insignificant compared to the background chloride concentration that's in the raw water.
Yeah, I would agree with that.
All right, gentlemen, we have another question here. How does one determine when there is a generator failure?
That's pretty wide open there. There could be different reasons why a generator fails, and are you talking about a complete failure or just a partial failure? Generally, it will be a lack of color being observed in the sight glass or any downline areas where you could view the generator effluent. That would be a sign. Some generators will have a pH probe on there. So if that pH is reading higher or significantly lower than what it typically is operating at, that may be an indication. Another indication could be when the operators are taking their residual chlorine dioxide measurements and not seeing a residual. So there's a lot of different ways to look at it. It really depends if it's a partial failure or total failure. Partial failure, you may not notice for a while. Like I said, you may see it in your residual chlorine dioxide measurements before you really see anything else. And then, one of the things you do, look at the color. If it looks where it should be, take a sample, do a generator effluent, and check the generator PLC logs to see if everything looks normal.
All right, thank you, Scott. Our next question is, why is chlorine dioxide most commonly used as a primary disinfectant as opposed to a secondary or residual disinfectant? Would there be any significant benefits or drawbacks to implementing chlorine dioxide as a secondary or residual disinfectant?
This is a
I
good
think
question.
you
Okay,
want to take that, Zach?
yeah, I can start, and then you can add on. So this is a good question, though. Why chlorine dioxide is mainly used primary rather than residual secondary? Because it reacts quickly with ingredients in water, especially for the pipe material, cast iron pipe material, for example. It can consume the chlorine dioxide quickly. So there's some difficulty to maintain the residue in the distribution system. So that is why normally it is used as a primary disinfectant rather than maintaining disinfectant. Well, that being said, there is some study being done in Canada comparing the use of chlorine dioxide as a residual in distribution system. So overall, the use of that, if the system can maintain distribution, can maintain the residue, it would be as effective, if not more, than in terms of control, total coliforms, and so on. Another very huge benefit would be its effectiveness in terms of controlling opportunistic pathogens, which is the emergent concern issue. These things like Legionella, mycobacteria, and other bacteria, which are usually tough to kill with either chlorine or monochloramine. But if you inactivate it with chlorine dioxide, it will be very effective. So sometimes in hospital system, you can use injected chlorine dioxide to boost the chlorine dioxide concentration in your system to control opportunistic pathogens. That's about Alan. You want to?
Yeah, I mean, I think the chlorite, MCl is the main reason chlorine dioxide is not used more so and at higher dosages. You do need to maintain the residual throughout the distribution network, and as some municipalities have quite long detention times, that could be an issue for chlorine dioxide. But that being said, it can still be used to supplement chlorine or the later monochloramine treatments upstream at the plant. Chlorine dioxide can still be used there to get that some initial higher level of disinfection and carry into the distribution network to some effect. And to Zach's point, we are seeing more chlorine dioxide usage at the premise plumbing, in industry and at hospitals, and where the water quality coming in isn't quite high enough of what they need. They're still getting some species of tolerant, emerging pathogens in those lines. Chlorine dioxide is one tool in the belt that can be used.
There have been a couple water plants in the U.S. over the years that have used chlorine dioxide as a secondary disinfectant into the distribution system. But one of the drawbacks, and goes to what Alan was saying, you need to have enough residual chlorine dioxide going out into the distribution. Unfortunately, there's an issue that does happen with chlorine dioxide, especially if you have too much in the distribution. when people open up their faucets and they aerate the water coming out, it can off gas a small amount of chlorine dioxide. And if they have new carpet or new furniture, those give off some volatile organic compounds, VOCs, and they can react with the small amounts of chlorine dioxide that's aerated, and it can produce some off-smelling odors. And that deters a lot of people from running chlorine dioxide as a disinfectant for the distribution system, because they don't want those complaints. But if they keep their dosages low enough, they don't have that issue.
Thank you, gentlemen. Our next question here is, we do not get good results from the chemiopalin test. We use the ampermetric, but was wondering if there was anything better or more effective.
Well, part of it goes to what is EPA and state approved for reporting purposes. In the US, ampermetric and the Cameo are approved by the US EPA for reporting chlorine dioxide and chlorine dioxide. No, sorry, chlorite, yeah, chlorite and chlorine dioxide. So really, those are your two choices. Some states still have the chlorine dioxide DPD method for chlorine dioxide, but for chlorite, it's amp titration or ion chromatography. And most people don't have the money or personnel to run an IC daily. I would recommend trying to reach out to your Palantast representative and see if they can help determine why you're not getting good results with your Cameo.
Thank you, Scott. Our next question, what are the key challenges in dosing and monitoring chlorine dioxide in large-scale water treatment systems?
Well, we've installed thousands of these systems, and really, I think it just starts at the front end, the planning stages, making sure we have a good site survey, understanding what the plant's needs are, and designing the equipment accordingly ahead of time. The equipment itself is very reliable, but if we've undersized the equipment from the get-go and we're not getting the residuals needed at the plant, everything needs to be redesigned. So it really starts in the initial stages here and taking some samples of the water to estimate the chlorine dioxide demand and the dosing requirement of these samples. So there's some work at the front end that really makes sure the rest of the process goes smoothly. I mean, the technology has been around for decades now, and it's if we know what we're trying to do, there's really no significant hurdle to implementing it. And then it's just a matter of putting the monitoring systems in place to monitor your residuals and make sure you're not overdosing. Anything to add to that, guys?
I would say, if it's a really large water plant, instead of trying to generate enough chlorine dioxide from one generator, it may be beneficial to have multiple smaller generators. That way, if need be, you could put different generators in different locations in the water treatment process. Also, that way you have kind of a backup if one of the systems goes down, that can at least partially treat.
All right. Thank you, Scott and Alan. And we have come to the last question in the queue so far. Is there a significant difference between chlorite manufactured from salt makeup and other methods when used as a precursor in the chlorite chlorine generation method?
Well, the main difference when you start with, I think they're asking the solid phase chlorite, is about 20% sodium chloride, salt mixed in with that. So, the generator will output a little higher levels of chloride salt, which may be, if a plant's already at high salinity levels, that might bump it up a little bit. But again, when chlorine dioxide itself is only being dosed at a ppm or so in the final treated water, that probably shouldn't have a large effect. More so, it's just the hazard of whoever's working with solid chlorite material. It's highly flammable. Even friction can ignite it. And in fact, we refuse to manufacture it, so we only make liquid grade sodium chlorite. There's been a lot of cases you can find online with disasters around solid sodium chlorite and improper handling and housekeeping.
All right, thank you, Alan. It appears we don't have any further questions in the Q&A chat. We'll just give folks a brief moment, just a last call for questions before we wrap things up here. All right. Well, seeing as there are no more questions, that concludes our webinar for today. Thank you, Scott, Zach, and Alan. As a follow-up, everyone will receive a recording of today's webinar, which we will send via email in the near future. For those wanting more information about chlorine dioxide in water treatment, you're invited to contact us using the email address shown on screen. Thank you again for joining us today, and have a great afternoon.
Thank you.
Thank you, everyone.